Welcome, everyone. Folks are just getting connected and we'll get started in just a moment. All right. Thank you so much for joining us tonight for our webinar on the geology of Baxter State Park. We are really thrilled to be hosting this. My name is Aaron McGuire and I'm the Executive Director of Friends of Baxter State Park. And this is the first event in our 2026 winter webinar series. So I want to start by welcoming all of our members who are watching tonight. Your support really does make events like this possible. So thank you from all of us. And if you're not already a member, it is quick and easy to join on our website at friendsofbaxter.org. And then you'll get all the emails and notices about events like this in the future, as well as helping to support the park. And there is a Join Us button in the upper right corner of every page on our website. And we would love to welcome you to our community of support for Baxter State Park. I want to offer a particularly warm welcome tonight to the park staff who are in attendance. Thank you. And to anyone watching who is joining one of our events for the first time, we are really glad you're here. So before we get started, just some quick housekeeping items. This event is in webinar format, so you can see and hear the presenters, but no one will be able to see or hear you. So you don't need to worry about the barking dog or the toddler meltdown in the background. None of us can see or hear it. But if you do have a question, you can simply click on the Q&A button at the bottom of your screen and a window will pop up where you'll be able to type your question. So please feel free to ask a question whenever it occurs to you and we will hold it for our Q&A session at the end. We will be sharing some slides this evening and anytime screen sharing is active, you will have the ability to zoom in or zoom out to fit the content to your own screen. So if you can't see the entire image, you can zoom out. And if you'd like to see more detail or something closer up, you can zoom in. And that will just affect your own screen and you can control that yourself. Those controls will only appear when we are showing slides. If you do need any tech assistance, please reach out in the meeting chat, which is also located at the bottom of your screen. I'll be monitoring the chat as well as Jam, our development director. Who is here on screen right now, and we will do our best to help you. So finally, just a heads up that this webinar is being recorded. So if you have a friend or family member who would like to watch it after the fact who wasn't able to make it tonight, we are recording and you can just reach out to us for the link to watch it afterward. So now I want to introduce our presenter for tonight, Dr. Lindsay Theis. And Lindsay is a senior geologist with the Maine Geological Survey. She also serves on the board of directors of the Kennebec Land Trust and is newsletter editor for the Geological Society of Maine. And perhaps closer to home for us, Lindsay is the geology instructor for our very own Maine Youth Wilderness Leadership Program for high school students, which takes place in Baxter State Park each summer. Lindsay lives in Augusta. She enjoys distance running, hiking, camping, and paddling. And we are very fortunate to have her here with us tonight. So with that, I'll hand it off to you, Lindsay. Thanks so much for being here.
Great, thanks for having me. Just gonna share my slides here, get that started up. And put that in slide mode. All right. Hopefully everyone can see that now. Like Aaron said, hi everybody. My name is Lindsay Theis. I work at the Maine Geological Survey, and I've been very lucky to do a little bit of work in educational outreach in Baxter. So I'm very happy and excited to be here to tell you a little bit about the geology of Baxter State Park. So let's get started. When I talk to land conservation groups, it seems like they are typically very focused on flora and fauna of the area, which is great. But I would like to make the argument that understanding the geology of an area is crucial to understanding its value as habitat. The geologic substrate influences flora resources such as soil and water, which in turn influences the fauna in that area. The geologic landscape creates various microclimates that can also influence habitat. And these two photos are not from Baxter, but they show how very subtle changes in substrate and slope aspect can drastically alter habitat within a very short distance. So I hope that any of you who are flora and or fauna enthusiasts we'll be able to make the connections between the geologic and landscape features that I talk about today and your knowledge of the park's various habitats. So I'll be giving a very brief overview of geology and landforms in Baxter State Park, starting with bedrock and moving forward in geologic time. I'm going to pick up Baxter's geologic story in the early Devonian period, a little over 400 million years ago. This is when most of the bedrock in this area formed. Then we will fast forward through millions of years of tectonic activity and erosion to the Quaternary period and the ice ages of the Pleistocene epoch about 2 million years ago. And then finally to the modern landscape that formed in the post-glacial Holocene epoch that started about 12,000 years ago. So this table is from our Guide to the Geology of Baxter State Park publication. And when I reference any of those, let me bring up my pointer here. When I reference anything from that publication, I'll note it in the slide with the table number or figure number so that you can look at them more closely during the presentation or later on, which brings me to my next slide, a little bit of business before we get started. If you don't already have a paper copy of our Geology of Baxter, and you would like to follow along on the maps, these are the bedrock and surficial geology maps that are included with this publication. You can type in this link on the screen. I know it's quite long, but you can also use your phone to scan this QR code, and that will take you to the digital Maine library, where you can download a free PDF of this entire publication and the maps. So I'll give everybody just a minute to do that if you'd like, and then I'll get started with the rest of the presentation. So go. And if you don't figure out how to access this right now, I'm going to have these links and the QR codes again at the very end of the presentation. And you can always just Google this and it should come right up. Okay, for the sake of time, I'm going to keep going here. Okay, so I don't have time to talk about all of the rocks in the park vicinity today. So I'll just be covering the ones that I feel are most important from oldest to youngest, starting with the Sebumic group. And this rock unit includes a variety of layered sedimentary rocks, which formed from the compaction and cementation of rocks and mineral particles derived from the erosion of other pre-existing rocks. These are also called stratified rocks in the Geology of Baxter publication. So why do these rocks have layers, as we can see in this photo of an example, not from the park, but it's a good example of the layers. Well, in the early Devonian, the area that is now Baxter State Park was covered by an ocean, and pulses of sediment called turbidity currents from erosion of a nearby landmass or landslides from shallower ocean waters settled out on the ocean floor. And this is a side view illustration of what that may have looked like. So picture a deep ocean and you've got pulses of sediment just from erosion or underwater landslides settling out on the deeper ocean floor. So if we were to zoom in and look at that area a little bit more closely, we might see that in each pulse of sediment, in each turbidity current, the larger or heavier sediments like sand settle out first, followed by the smaller, lighter sediments like silt and clay. And each pulse of sediment forms a graded bed, which is what geologists call this package of sand to finer sediments. And graded bedding is very helpful for geologists because even if the rocks are deformed later on, they can help tell which way was up when the sediments were originally deposited on the bottom of the ocean based on this grading. So the subumic group includes layers of sandstone and siltstone and slate, and these rocks are mostly found in the northwestern part of the park in the blue map unit labeled DS. So this is just a snippet from that bedrock geology map from our publication. So if you would like to see these rocks in person, the best place to do that in the park is where the Freeze Out Trail crosses Trout Brook north of the Trout Farm campground, and I have that circled there in red. So now that we know how these rocks have formed, let's take a closer look at what they look like. So the light gray layers in this photo are sandstone. And then the dark gray layers are slate, which is made of the finer particles. And so each couplet of sandstone and slate is a graded bed from one turbidity current event. So you can see there's a lot of those here. And you may notice how there's a very sharp boundary between the top of a slate layer and the bottom of a sandstone layer, but the boundary between the top of a sandstone layer and that gradually transitions to slate. So this illustrates the flush of sediments from one turbidity current. And because this is a natural process, you may notice that some of the graded beds are quite neat and easy to pick out, and some of them are not. Like down here, they're very messy because we have a variety of sediments and not every turbidity current is the same. And that's figure 5 in the book, if you want to look at that later. So after the subumic group rocks formed, tectonic activity continued in the area, which caused the ocean to become shallower, and a sandy delta was built into the ocean over the subumic group sediments. This sand compacted and lithified to form the Matagamon sandstone, and that's what we see here in this picture. So it's just what it sounds like. It's sand that's been compacted to become a rock. And this is the teal unit over here on this map. So this rock type is pretty interesting because it does contain fossils, mostly brachiopods, which you can see down here look like clamshells, but they're not actually clams. So if you would like to check out some Matagamon sandstone, unfortunately, the best places to see it are actually just outside of the park, along the road from Patton or at Grand Lake Matagamon Dam. Soon after the Matagamon sandstone was deposited, a period of intense volcanic activity ensued. And the exact location of the source volcano or volcanoes is unknown, but pulses of hot ash and pumice and froth were deposited, compacted, and cooled to form layers of volcanic rock known as the traveler rhyolite, which is my personal favorite rock in the park. It's estimated that the traveler rhyolite deposit is at least 80 cubic miles. And for comparison, the deposits from the 1980 Mount St. Helens eruption were less than 1/10 of a cubic mile. So the traveler eruptions must have been incredible. Traveler rhyolite is a type of extrusive volcanic rock comprised of volcanic material that cooled to form rock at the Earth's surface. So extrusive means at the Earth's surface, and later on we'll talk about intrusive volcanic rocks which form beneath the Earth's surface. So traveler rhyolite is divided into 2 distinct types, but the best examples in the park are of the black cat member of traveler rhyolite, which is the lighter red unit on the bedrock geology map labeled DTB. So that's what you most commonly see in the South Branch Ponds area. This rock has some really interesting features which are easy to view from many of the trails in the South Branch Ponds area. And one of the most noticeable characteristics is layering that represents individual eruption events. So this right photo is from the Ledges Trail just north of South Branch Campground. Very nice short little walk. And each bench in this photo is a rock layer from an individual eruption event that's been accentuated by later erosion. It's happened over millions of years. Another very interesting and very noticeable characteristic of traveler rhyolite is columns, or columnar jointing, as we more formally call it in geology. And these form due to the shrinking of the rock as the ash flow cooled. These columns are easy to see in many cliff exposures if you're out paddling on any of the South Branch Ponds area or hiking in the area. And lastly, if you look very closely at an exposure of traveler rhyolite, you may notice what we call compaction foliation, which is a very, very fine layered structure in the rock that formed as subsequent ash flows added weight and compacted the underlying ash flows. So if you were to cut open a sample of a rock, this is a sample that we have in our collection. So I cut that open and polished it up so it looks real nice. The layering is very easy to see. And the brown streaks that we see here that are now flattened were originally pieces of pumice within that ash flow. So you can imagine the compaction that was taking place there. If you would like a more detailed tour of traveler rhyolite features, you can follow my guided hike of the Ledges Trail from the South Branch Pond campground. That's the link there. And but I'll show you how to access similar guided hike publications for the Baxter area that we have at the survey at the end of the presentation. So if you don't get that now, you'll be able to get that later. So after the traveler volcanic eruptions, the magma remaining in the volcanic chamber below the volcano cooled beneath the Earth's surface to form an intrusive volcanic rock known as Katahdin granite. And we can find various types of granite all over Maine. But what makes Katahdin granite so special? Why does it form the highest peak in the state? Well, most Katahdin granite is regular old plain Jane light gray granite with medium-sized mineral grains, as we can see in this left photo. Doesn't look very special. It could be curbing in a parking lot anywhere. And this is the tan unit on the bedrock geology map that takes up most of the southern part of the park. However, there was an area at the very top of the magma chamber that cooled and crystallized very quickly because it was much closer to the colder conditions at the Earth's surface. And when magma cools quickly, the minerals don't have as much time to grow, resulting in finer grained granite with interlocking quartz and feldspar crystals known as granophyric texture. And the difference between these two types of Katahdin granite are pretty clear in these photos. In the left one, you can see the individual mineral crystals. In the right one, not so much. So they're all much smaller. So finer grained granites, like the granophyric phase of Katahdin granite, are more resistant to erosion due to their dense structure, thus forming many of the highest peaks in the park, which are easy to spot on the bedrock geologic map due to they're the darker tan unit, so they're easier to pick out there. It also has a pink to reddish appearance due to changes in the feldspar minerals in the rock that incorporates tiny hematite grains, which is iron oxide. So there's a very detailed description of that process in the Geology of Baxter publication if you'd like to read more about that. So while you're hiking Katahdin, you may notice this change to the granophyric phase starting at about 4,500 feet elevation. Or you may be like me and gasping for air and not quite paying that close of attention. Just know that when you reach the tablelands, you're traversing the granophyric phase of the Katahdin granite, and that's why it's the highest peak in Maine. So after the Katahdin granite formed, millions of years elapsed during which more tectonic activity deformed the existing rocks and a lot of erosion took place. And the Trout Valley Formation is comprised of a variety of eroded sediments that were deposited in shallow brackish waters that covered the area at the end of this transition. And these sediments were compacted and cemented to form a variety of sedimentary rocks found in these yellow and gray map units here just to the northwest of the South Branch Ponds area. So the left photo is a cliff exposure of mostly sandstone along South Branch Ponds Brook. A prominent part of the Trout Valley Formation is the Gifford conglomerate, which is a great idea for an ice cream flavor. But it is actually a sedimentary rock comprised of sand and pebble and cobble gravel. And the best place to see these rocks is actually in exposures along South Branch Ponds Brook, as these people are finding out here. And you can find cobbles of traveler rhyolites in this rock, which are some of these lighter colored cobbles in a close-up of this Gifford conglomerate. So there's also layers of finer grained sedimentary rocks interspersed with the conglomerate. In a geologic traverse of South Branch Ponds Brook during late summer low flow conditions, as these folks are doing here, is a classic experience for Maine geology students and enthusiasts. And you can actually find an illustrated guide of how to do that in the Geology of Baxter publication that I mentioned earlier. The Trout Valley Formation is also well known for its fossils, which includes the Maine state fossil Pertica quadriferia, which can be found in shales of the Trout Valley Formation as shown in this right photo from our MGS collection. So Pertica was a plant that grew in brackish marsh waters. This is what people think it may have looked like. And fragments fell into the marsh to the floor and were buried and preserved by the sediments. So it's a pretty rare fossil found in only 4 places worldwide. So if you happen to come across it, please leave it where you found it. And it's important because it helps geologists estimate the age of the Trout Valley Formation, which is a little younger than 400 million years old. And it represents the early evolution of vascular land plants. So pretty cool fossil in the Trout Valley Formation. Okay, so now that we know a little about the bedrock of Baxter, let's switch gears to the park's surficial geology. And if you're not familiar with surficial geology, that includes all of the earth materials overlying bedrock that were deposited by glaciers during the last ice age, or areas modified by fluvial and or biological processes in the post-glacial times. So the park's landscape was pretty much established by about 10 million years ago. But then a series of ice sheets moved over the area during the Pleistocene, refining the landscape through glacial erosion and deposition. So the the landforms and deposits that we see in the park today are a result of the last glacial advance and retreat that took place about 25 to 12,000 years ago, as we can see in this figure here. So there was a couple of glaciations before that, but the most recent one is most important to what we see today. So the ice sheet was actually thick enough to cover the state's highest peaks, including Katahdin. And we know that glaciers were gone from Baxter by about 13,000 years ago from radiocarbon dating of early lake bottom sediments in the area, and another dating methodology that can estimate when bedrock was exposed after the glacier retreated from the area. I'm going to divide Baxter's surficial geology and glacial landforms into those created by erosion and those created by deposition. Let's start with features created by erosion. Much of Maine's landscape has been sculpted by the power of glacial scouring and plucking. And this process occurs as glacial ice flows over and around bedrock highs. So sediments stuck in the bottom of the ice, which aren't really shown in this illustration. Ice is actually usually really dirty, but they didn't include that here so that you could see what was going on. So those sediments stuck in the ice scour the bedrock as they're dragged over, And then on the down ice side of the obstruction, chunks of bedrock freeze onto the bottom of the glacier and are plucked off and carried away in the ice. And so this process creates gentle up ice slopes and steep down ice slopes known as Stoss and Lee landforms. And we can use our knowledge of this process and the resulting landscape to infer what the former glacial ice flow directions were. So on this map of the northeast corner of the park, here's Grand Lake Matagamon. Several peaks such as Billfish and Trout and Horse Mountain are all good examples of Stoss and Lee landforms. And they provide a clue that ice flow was generally from the northwest to the southeast in this area because of their steeper southeast facing slopes. Before I move on, I want to note that all of the maps I'll be using to illustrate various glacial landforms are topographic hillshades derived from LiDAR topographic data. And if you're not familiar with LiDAR, it's basically a laser scan of the Earth's surface from planes that can be processed to remove buildings and tree cover, resulting in very detailed bare Earth topography. LiDAR is a very essential tool in surficial geology. And I want to note that if you do read the Geology of Baxter publication, the authors did not have the benefit of LiDAR when they wrote the books, which may have influenced some of their interpretations. So if you're not familiar with LiDAR, Google it. It's really interesting. Makes fantastic maps. Couldn't do work without it. And here's a nice view of Horse Mountain's glacially plucked cliffs from Grand Lake Matagamon. Glacial erosion that's focused in valleys tends to create U-shaped valleys over time through plucking and scouring, as opposed to the typical V-shaped valleys created by fluvial or stream erosion. So the Wasatacook and South Branch Ponds valleys are really nice examples of U-shaped valleys in the park, as marked by this dash line, the red dash line in the photos. So if you're out in a canoe or kayak on either of these lakes, you'll be able to see that very well. It's a little harder if you're not on the water. Cirques are bowl-shaped depressions formed by glacial plucking and scouring at the headwaters of a glaciated valley. And the right diagram shows a side view of what happens during cirque formation. Glacial ice freezes to the bedrock and plucks it off of the valley wall, transforming a V-shaped valley to a bowl shape and steepening the valley walls over time. And of course, the basins on the east side of Katahdin, as we can see here, are great examples of cirques. And tarns are ponds that form in the glacially scoured depressions after deglaciation, often in the bottom of a cirque. And of course, Chimney Pond is a classic example of a tarn. So here's a nice ground view of Katahdin's bowl-shaped cirques, and this is from the Route 11 overlook. I think somebody had a really nice telephoto lens for this photo. And then, of course, looking down into the South Basin cirque and the Chimney Pond tarn from the Katahdin ridgeline. So great classic examples of those two features. And then, of course, we have arêtes. Arêtes are narrow ridges that form due to glacial plucking and erosion on either side of a ridgeline. So not just one side, but both sides. And so they're very steep, narrow ridges. And the word means stop in French, which is what you might want to do when you're hiking the knife edge, which is a classic arête ridgeline, as you can see right here. And in this photo as well, just very steep on both sides. And Hamlin Ridgeline over here is also a nice arête, but not as extreme or fear-inducing, I think. So striations are harder to see in the park. They're not as common, but they're scratches and gouges left on bedrock by that rock debris stuck in the ice that I mentioned earlier. And similar to Stoss and Lee landforms, they're really good evidence of former ice flow direction. So the right picture is of striations on Madagamon sandstone, which are parallel. Hope you can see that. The picture is a little fuzzy. They're parallel to the pencil and compass in the photo and parallel to the former ice flow direction, which was from bottom right to top left in this photo. So not all bedrock exposures will have striations. Weathering can erase them over time, especially on higher peaks where there's more extreme weathering conditions. So finer grained rocks like those in the Sebumic group and Madagamon sandstone that are these lower elevations tend to have better striation preservation. And that trend is clear if you look at the surficial geology map. The vast majority of striations are in the northern part of the park or just outside of the park, which are marked by these arrow symbols. And if you remember the bedrock that we saw earlier, this is all Sebumic group over here and Madagamon sandstone down here. So that definitely makes sense with these observations. One of my personal favorites is meltwater channels. They're so cool. So as the ice was retreating from the area, meltwater channels were carved into glacial deposits by torrents rushing glacial meltwater. And these channels usually formed at or near the edge of the glacier, as we can see in this little side view illustration on the left. So they give us the idea of the pattern or direction of glacial retreat. In this area around Trout Brook, so here's the South Branch Ponds area, and here's Trout Brook. This has many, many great examples of glacial meltwater channels that imply northwesterly glacial retreat as a series of channels follow that direction. So you can just imagine a massive glacier here with water flowing along the edge. And as the glacier melted away to the northwest, new channels formed as that boundary moved itself. So these channels often don't make sense when you look at them in the modern landscape in comparison to modern stream channels because they can start and stop abruptly and they flow across the slope instead of down the slope. So it's pretty easy to spot them on LiDAR if you know what you're looking for. And these channels are usually dry in modern times. So if you were to go to the bottom of one of these channels, it might be bouldery and have trees and vegetation in it. But if you were to take away those trees, it might sort of appear like a modern stream channel, but without the water. So I like to call them ghost channels. And meltwater channels are often hard to pick out without LiDAR, but these channels are so spectacular that geologists recognize them on air photos long before they had LiDAR. So as I mentioned before, the Baxter guide authors did not have LiDAR at the time that they wrote that, but they still knew that these existed from looking at air photos. They're just that great. So now that we've taken a look at how glacial processes have sculpted the landscape, let's take a look at materials and landforms related to glacial deposition. And if you look at the surficial geology map, which I have a snippet of here, most of it is teal colored, which is glacial till. And if you've walked around anywhere in Maine, you're probably already very familiar with till. It's a chaotic mix of rock debris from clay to boulders that was transported and deposited by glacial ice. And we've got an example of that right here. And this is not from the park because we don't have big gravel pits in the park where you would see an exposure like this. You have to use your imagination a little bit there. A little bit. So till blankets the bedrock in much of the state, and Baxter is no different. And it can be compact, as in this left photo. And this variation is commonly called hardpan, and it's usually found on up ice slopes where the sediments in the ice were smeared against the hillside under great pressure. And then till can also be loose and stony, as in this right photo. Moraines are ridges of till deposited at the very edge of the glacier. And glacial ice is typically flowing even when it's retreating. So when the ice retreat pauses, rock debris is still brought to the edge of the ice by the flowing activity of the ice and dumped either from the edge or the top or from the base. And or the glacier can shove material into a ridge if it grows and re-advances for a short period. And this right photo shows a small moraine ridge at the edge of a modern glacier. So if we move over to Baxter, the large basin ponds moraine that we can see here on this LiDAR map was likely created by a tongue of ice in this adjacent valley here. And you can see this is a view of that moraine. So I think I'm pointing to that. The arrow is linking up those two locations. So I think that, excuse me, this moraine is crossed by the Huron-Taylor and Chimney Ponds Trail. And this is a view of the moraine from Blueberry Knoll. And similarly, a series of moraines on the south slope of Katahdin, which hopefully you can see here, and outline those with my pointer. These were likely created as the glacier thinned and the ice surface lowered in this valley to the south of Katahdin. So the moraines become younger as you descend this side of the mountain. So glaciofluvial deposits are sand and gravel deposited by glacial meltwater. And these are the orange and red units that you see on the surficial map. Outwash is sand and gravel deposited by meltwater streams flowing away from the edge of the glacier. And the left photo shows a modern day example of some sand and gravel in a modern outwash plain. So outwash areas have a relatively flat surface, but sometimes they'll have round depressions called kettles that were formed by chunks of ice that fell off the glacier, were buried in the outwash, and later melted, leaving a depression. So the right map is a LiDAR map of the Six Ponds Valley southeast of Wasatacook Lake. And these flat outwash areas are marked with an O. And they were probably much larger, but they were eroded as the modern stream network became established. And so it removed some of the materials. But you can see some of the bumpy texture, which is probably kettles that I just described earlier. So there were chunks of ice in here, they melted away, and giving it that bumpy topography. But most people are familiar with eskers. They're sand and gravel ridges deposited by meltwater flowing in tunnels at the base of the glacier. So when the ice melted away, a long, narrow ridge is left behind, sort of like an inverted stream bed. And there's a very nice esker ridge in the Six Ponds Valley, which I've marked with an E here. Hope you can see that there. And the left photo is a ground level view of an esker segment. So glaciofluvial deposits, both outwash and eskers, are very important because they make excellent aquifers and they can be used as an aggregate source for things like road construction, which they're not going to be mined in the park, but elsewhere in the state, they're often used for construction materials. Okay, so the last part of my presentation will cover geologic processes that have been taking place in the post-glacial era known as the Holocene. And in the time between deglaciation and establishment of thick forest cover, there was likely a lot of fluvial erosion as modern stream networks became established. Alluvial fans are fan-shaped landforms that that provide evidence of this erosion. And they were formed when sediments carried by higher energy mountain streams were deposited on the valley floor, as shown in this modern day example, which is from somewhere in the western US where there's no trees to block anything. So the South Branch Valley north of the campground, so here's the pond and the campground is right about here. This area was actually dammed by two alluvial fans, which I have outlined here in red, that encroached on the north end of the valley from both sides. And the eastern fan also makes a nice campground area. So the campground, again, is right here because it's less bouldery than the nearby areas that are covered with glacial till and rock debris. That's a lot stonier. In addition, a large alluvial fan at the mouth of Howe Brook. So if we move a little bit farther south in this valley, we can see there's a very large alluvial fan that separates upper and lower South Branch ponds, which was likely one large lake before this alluvial fan formed just after deglaciation. And there's a nice view of this fan from the North Traveler Trail. I think it was probably about here when I took that photo. And this is a panorama of the Howe Brook alluvial fan from where it meets the valley wall along the Pogie Notch Trail on the south side of the landform. So this gentle, easier grade is, and easier walking is always a welcome reprieve from the typical technical and rocky trails. So you can see the vast difference in the alluvial fan grade as opposed to the valley wall here on the right. I think I'd rather be hiking on this at the end of a long day. Mass wasting is a term for the downslope of movement of earth materials due to gravity, and there's examples of several types in Baxter State Park. Rockfalls are the simplest and probably most common type of mass wasting in the park. And most rockfalls happen when water repeatedly freezes and thaws and cracks, slowly wedging a piece of rock apart until gravity takes over and boom. So there's been plenty of rock falls in modern times in the park, but they were likely much more common in the early Holocene when the climate was still relatively cold and freeze-thaw cycles were more intense. LiDAR can help geologists find older rockfalls and rockfall paths that are now hidden by vegetation. So I've got a nice LiDAR map over here. And this is for part of Mount OJI. So I have the eye in Mount OJI circled here, and the LiDAR shows us the path and the distance traveled by the rocks that toppled and slid from the eye area. So they went all the way down to here where they stopped. So they probably traveled about half a mile based on our scale up here. And an area just to the east is really similar, but the rocks didn't travel as far for some reason. And sometimes the rockfall paths become surface water drainage paths later on that are accentuated by subsequent fluvial erosion. So the O in OJI is over here, and that rockfall path was further carved out by water erosion later on, and it's now more of a stream valley. So what happens to all of those rocks? Well, piles of glacially plucked rocks can be accentuated by rockfalls. So on the down ice side of Stoss and Lee landforms, there's often still a steep cliff where you have rockfalls continuing through modern times. And these deposits of bare rocky areas on the downslope sides are known as talus. And so the right photo shows a nice example of a talus field at the base of a cliff on Horse Mountain. And you usually remember hiking across talus because it's a little tough on the ankles. So perhaps you remember some of those areas in the park. So there's several large landslides in Baxter that are really only recognizable with LiDAR. And this is probably the most spectacular example, I think, from South Turner Mountain. So geologists did suspect, if you read the Geology of Baxter publication, they did suspect that there was a large landslide near the peak of South Turner, and LiDAR has confirmed that. So this must have been a really impressive event. So this area is what we would call a translational landslide, where one block of earth materials moved downslope together as one unit and basically maintained its original shape. So it's almost like a piece of the side of the mountain just went down to a new spot. So large slides like this may have been triggered by wet conditions, an earthquake, or a combination of the two, probably a combination of the two. And this is what that looks like So you pass right by it if you're hiking up to South Turner Mountain. And of course, the mountainsides of Baxter State Park are littered with scars from avalanches and debris flows that appear as tan streaks on air and land-based photos, as we can see here. So Mount OJI and the Abel Slide are classic examples. And most people are familiar with the concept of avalanches, but debris flows are a type of landslide that require wet conditions during which loose earth materials such as till and rock debris move downslope as a wet slurry. So debris flows can start as rock falls or avalanches that gather momentum as they move downslope, mobilizing other materials almost like a snowball effect and creating a larger mass movement. So sometimes it's difficult to tell exactly what happened in any of these conditions. And sometimes it's difficult to discern what is an avalanche or a debris flow scar from a stream gully or stream erosion because drainages may become established in these slide paths after the mass wasting event, as I mentioned earlier. And yeah, because it's a natural process, it's hard to tell exactly what happened for each of these scars that we can see on the air photos unless somebody actually witnessed the event. And I'm not sure anyone would really want to do that. But there's plenty of great examples that we can see from afar. So that wraps up our very brief Baxter geology tour. And the Geology of Baxter Park publication is a great resource if you'd like to learn more about the park's geology. And you can download a PDF from this QR code or just go to our website or Google it. It's very easy to find. We also have shorter, more specific geologic guides for the park, as I mentioned, the Ledges Trail publication earlier, and that can be found in our Geologic Facts and Localities series, which you can find at this website or at this QR code. And this is the QR code for Geology of Baxter State Park, or you can always send me a question via email. So that's it. I can answer any questions if anyone has any.
Thanks so much, Lindsay. Outstanding. Sure. Yeah, there are a few questions in the Q&A feature. I think we have 4 in there so far. And if you have a question that you haven't typed in yet, now's your chance. But we'll get started on the 4 that we have already. So first question, Lindsay, how long a period of time does a turbidity current occur? How long did it take to form one of these sedimentary layers? Months, years, millions of years?
I think the individual turbidity currents would be a pretty quick event. So you can see how many there were just in that one photo. So those would be one pulse of sediment. And I think it would depend on the source. If you have a landslide, maybe that would happen less frequently than maybe a pulse of sediment coming from a storm event or something like that. So it'd probably be pretty variable, but there were a lot of them to create that many layers of rock. So really a geologically active environment.
Yeah. Okay, thanks. Next question. Was the ash extruded onto land or underwater? And I think this is referring to the ash from the traveler eruptions when you were talking about ash flows. I think that's the part of your presentation.
That's a good question. I think that they were subaqueous. I'd have to look that up again now.
So that means underwater. Yeah.
Yeah, sorry.
Okay. Yeah, got it. Okay, great. Thanks. Good question. Are there other areas of columnar jointing other than the one shown in the photo? The person that asked the question has been to that spot. Yeah.
Yeah, so you can actually see the top of the columns in this photo right here. So this is on the North Traveler Trail. So if you look at them from above, they have multi-sided shape, but it's not always the same number of sides. But you can see them. Barrel Ridge is also a great hike to see columnar jointing. You can see it there's a viewpoint that's sort of up part of the North Traveler Trail that has a 360-degree view, but not quite to the peak. And you can see a lot of columnar jointing from there. So yeah, anywhere on the North Traveler Trail is really, really easy to see, or yeah, paddling on the ponds, looking up at the surrounding mountainside, you'll see that there.
Great. Okay. Yeah, awesome. That's a great photo. I hadn't noticed that in the one that's up on screen now, but that's awesome. All right, next question. Did the cirques on Katahdin form when continental scale glaciers were overriding the area, or was Katahdin a source of glacial ice between ice sheet advances or after the ice sheets retreated north?
Oh, that's a tricky question. I think people are still trying to figure that out. So there's evidence that Katahdin was covered by glacial ice during the last ice age. So um, they're not sure if those were formed beforehand or and just accentuated later on. But yeah, if I can, whoever asked that question, if you would like more detailed information about that, I can send you some journal articles about that. I think people are still sort of trying to figure that out exactly. There's a few different ideas, or a couple of different ideas about that.
Yeah, even me as a very non-geologist, I've heard some very emphatic opinions in both directions on that one in the last several years. Yeah, definitely
Yeah.
multiple schools of thought, but yeah, great question. Next question. Any interesting info about the Daisy Kidney Ponds geology, and a compliment on the excellent talk
Oh, thank
from that
you.
questioner. Yeah.
Gosh, I guess I haven't, yeah, that we I haven't covered that at all. That would be a good one to add. I just look at the map really quick here. I think probably because things are in the southern part of the park, um, the the bedrock geology is that plain Jane Katahdin granite, so it's not as flashy as other areas, and it just kind of stony till in a lot of those areas. But yeah, I know that those are really popular, so that's a great suggestion to do a little bit more thorough. There's some good glaciofluvial deposits to the north of that area. So have to see what the trails cross. I've only been there in the winter, so it's harder to make a geology guide when you can't see anything. So I'll have to
Absolutely.
go back in the summer sometime.
Yeah, and that's a great lead into the next question. The question is, will there be an update to the guide, the Geology of Baxter book that would include LiDAR?
That would be my dream. That would be fantastic to do. Obviously, this was, the culmination of two geologists' lifetime of work in the park. And yeah, I think it would be fantastic if you'd like to call the department commissioner and suggest that to them that we should use our funding for a new Baxter publication, that would be great. I would I would fully support that. But yeah, we don't have any immediate plans to do that. We still have boxes and boxes of this guide. So if you want one, please order one.
Yeah, and you said they're free, right? You'll
Yes.
place yeah.
Yeah.
So if you want a hard copy, yeah, they're free and it's excellent. We use that book for our summer youth leadership
Yeah.
program, and it's
Yeah. Free
outstanding.
free within reason. If you want, one or two copies, that's great. If you want 50, we'll have to figure something out
Got
for
it. Yes,
postage. Yeah.
sounds totally fair. Follow up, next question. If the Gifford conglomerate were an actual ice cream, what would the ingredients be?
Oh my gosh. It should be, yeah, it should be some sort of ice, maybe vanilla or chocolate, or probably chocolate with those little chocolate candies that look like rocks. Don't you think that would be great?
Yeah,
Because I
the
think,
fake rock candy. I
yeah,
love that stuff. Yeah, absolutely. Yeah, that sounds great. With a LiDAR hillshade, I can see a few blobs of rounded upland rising out of the wetlands in the Klondike. Do you have any idea what
oh,
those are?
yeah. So those could be paraglacial features. So Um, paraglacial means, close to ice. And so the environment right after deglaciation was probably very cold, tundra-like, sort of like modern day Alaska. And you can get these features that form from ice growing within the soil. They're called pingos. So they are these ice domed hills, and then when they melt and collapse, they create these rings that are left behind. And so it could be a pingo scar, or it could just be something random. You'd have to go out there and check it out in person. But I have found pingos and other paraglacial features in other parts of the state, so it wouldn't be unusual.
Yeah, very cool. Yeah, that's a very difficult but really fun bushwhack in there if you get a chance to check those out. Yeah. Great questions coming in. Thank you all for these excellent questions. I think they're actually accumulating faster than we're answering them, so we may need to cut them off here in a few minutes. But can you explain a bit as to how the sharp downslope profile is formed on the southeast slopes of ridges where plucked material gathers?
Yeah, so I can go into a little bit more detail than I did in that slide. So as the ice is trying to flow around a bedrock obstruction, there's a lot of pressure at the base of the ice, which actually causes it to melt a little bit on the up ice side. And so then that melted water moves through, groundwater flow or at the base of the ice around to the front of the obstruction where it refreezes because it's no longer under that pressure. And then it freezes onto the rock. And then as the ice flows, it yanks it off and transports it away. So hopefully that makes sense. So the rock already needs to be fractured to some extent. If it's really solid rock, it's a little bit harder for that plucking to take place, but most rock in Maine is pretty fractured to some extent, so makes the plucking process a little bit easier. So melting on the up ice side, refreezing on the down ice side, boom, plucks it away.
Great, thank you. So this next question, I think I may have some info to share about this, but hiking from Chimney Pond to Roaring Brook, we saw many large stones with cavities that looked almost like blast markings. We were calling them space eggs. Can you explain these formations?
Oh yeah, so
yeah.
those might be what are called vugs in the rock, which are common in the granophyric Katahdin granite, and you can read. I don't have time to go into that, but if you just download this, there's a very detailed description of how those form right in this publication. So
very, very cool. Yeah, I've seen a few of those too and was mystified. So I'll
yeah, and they can fill with minerals, so they might be filled with other minerals that aren't typically part of the rock, or they can be empty.
I'm going to skip ahead to another question also about the Chimney Pond Trail that I think has a different answer. This is what I thought the other question was getting to. On the hike up to Chimney Pond, there are round structures in the rock about 1 foot in diameter. I wonder if they're impact sites. Any ideas? And I think this is actually, these are blast markings they would dynamite rocks in the trail. They have like fractures coming out from the center.
Oh yeah.
Yeah, do you know what I mean? Yeah.
Yeah, I think I've seen that on social media, and yeah, I don't have a geologic explanation for that. So yeah, I think if they're probably that's more likely.
That was pre Baxter State Park existence trail work, and that was they'd drill a hole in the rock, put in a stick of dynamite, and run. And so those fractures are really distinctive. You can see, I think I lost count at 70 or 80 of them on the Chimney Pond Trail the last time I hiked.
Must have been interesting and fun, but
yeah, absolutely.
Not very safe.
Oh, good question, Beth. Thanks. Okay, next question. This person's wondering about the total amount of material deposited by the Traveler eruption. He had read 500 to 900 cubic kilometers. And did you say you had an amount in cubic miles, right?
Yeah, so the estimate is about 80 cubic miles. So like I said, Mount St. Helens was like 1/10 of a cubic mile, so it was huge.
Wow. Yeah.
Huge eruption.
That's amazing. Yeah. Okay. I don't know off the top of my head how to convert cubic miles to cubic kilometers, but yeah, 80 cubic miles done. That's your answer. Yeah. No, thanks. That's great. Is the conglomerate on the top of Wasatacook Mountain different from the one found over by South Branch? Wasada Cook
Oh,
Mountain is a bushwhack. I don't know if you've been up there,
no,
Lindsay. Yeah.
I don't think that it is a conglomerate. I think that that is also, oh, where's my map here? I have to refresh my memory. Oh, wait. DH. I can't quite tell from this map. It's definitely not a conglomerate. Sorry.
Okay.
Yeah, that should be top of Wasada Cook Mountain should be Katahdin granite. So, um,
Okay.
there is conglomerate there, then these guys were wrong. So I have not been up there.
Got it. Yeah, an exciting bushwhack. Great question. How long does it take for vegetation to become established after a glacier recedes? Now that's a maybe a
Ooh,
different specialty. Not
yeah,
sure.
that's an interesting question. I think it probably depends on the area, but like I said, there's actually, if you look at the surficial geology map, you'll see there are some radiocarbon ages listed. So um, there was a sample taken from the bottom of Upper South Branch Pond, if you look at the surficial geology map. And so they took organic fragments from that and radiocarbon dated them to determine, when the ice was gone. And so that was about 12,800 something years ago. So that's pretty quick. If you compare that with some of the other glacial retreat dating methodologies, just a few hundred years. So pretty fast.
Yeah. Yeah. That's plants are pretty amazing and at moving in quickly. Couple questions about Katahdin. Is there any evidence that Katahdin was a former volcano?
Well, it was part it's a volcanic rock, but it was magma, so volcanic material, liquid hot magma that it cooled beneath the Earth's surface. So it was part of the magma chamber that would have fed a volcano, or it didn't become a volcano, but it was sort of associated with just after the traveler rhyolite
Mhm.
um, eruptions, but different type of magma. So.
Okay, great. And then the next question is about what evidence is there that ice covered the top of Katahdin?
Yes.
This is
So,
getting to that debate. Yep.
yeah, people have found different rock types up there. So, I didn't mention erratics here, but an erratic is any rock, a rock of any size. And in Maine, people tend to think of them as huge boulders that are more visible on the landscape, but they're a rock that is significantly different from the underlying bedrock. So, maybe they found a type of metamorphic or sedimentary rock on the top of Katahdin, and so it's much different from the Katahdin granite. And the only way it could have gotten there was through a glacier or by a glacier.
Got it. Yes. That sounds quite convincing. Um, has LiDAR changed any of the peak height measurements? Is it being used in that way?
Oh, that's a good question. I'm sure it's refined it a little bit. I'm sure it depends, how many people stack more rocks on that top of the cairn on top of Katahdin. Um, But yeah, that's a good question. I'm not sure the answer of that if it's actually changed the height of Katahdin, but I know
Yeah.
it's made the geology easier to see.
Yeah. Um, yeah, absolutely. Okay, let's see. Are there any original height estimates on the traveler volcanoes and surrounding mountains when they erupted? Any sense of
Oh
how big
no,
those
yeah.
were? Yeah.
That would be really interesting. And as far as I can tell from everything that I've read, they're not we can't even really pinpoint where the original volcano was within that area. There's just been too much erosion that's taken place over the last 400 million years. So that would be cool to know. But yeah, there's no knowledge of that as far as I know.
Yeah. Okay, great. Couple folks very helpfully converted cubic miles to cubic kilometers for us. So for the
Oh,
person who asked that question, 80 cubic miles equals 334 cubic kilometers. So yeah, a little, yeah, that's how that converts out.
yeah.
Thank you, Bill and Kathy, for converting that for us. Let's see. Are you related to the famous geologist C.V. Theis from the Theis equation, 1935?
Maybe, but yeah, I don't have any direct knowledge of that.
Yeah, yeah,
That would be cool. Maybe it's yeah,
yeah.
somewhere, but
Well, you keep us posted if that pops up in your family tree. Yeah, very cool. Let's see. Question about the Grand Falls area. Why does it look so different? Why does the Grand Falls area look so different from others? Um, I'm not sure if you've spent much time down there.
no, like
Yeah.
yeah, I'm sorry, I haven't spent much time there.
Lower Wasatch Extreme. It is quite different, yeah, than other areas of the park. That's it's yeah, it's several miles down from where the Russell Trail crosses, and it is really dramatic and distinctive. So yeah, I
I'll have to do that this summer and get back to you.
yeah, it's a really worthwhile day hike. Um, okay, down to the last few questions. Does the Katahdin granite contact the traveler rhyolite?
Yes, it does.
Okay.
And there's much more detailed description of that relationship in here. So I just encourage you to read that.
Yeah.
How the rocks are interrelated to each other. There's a section at the end of the bedrock geology section that very much more eloquently than I will put that story together for you.
Yeah. Okay. Yeah. Thank you. Thank you for we've got two more, and thank you, Lindsay, for taking all these questions.
Yeah,
And
no
thank you.
problem.
Yeah, thank you everyone who's asked these excellent questions too. All right, last two. Slightly raised on the trail to Chimney Pond are circular and about 2 to 4 feet in diameter, resembling a barnacle in vertical view with radial fracturing. Is there an explanation for these? And I think those are the
Yeah,
dynamite blast marks that we were
yeah, I
talking
think
about
that's the same
earlier.
thing. Yeah.
Yeah, that's about how big they are. And yeah, they took the points off of those bigger rocks so that they could get pre-park days, they could get livestock up there and haul equipment and stuff. There were burros and pack animals that used to move things around up to Chimney and into Russell Pond, and a lot of that blasting was done to make the going easier for those animals.
Interesting.
Yeah. So last question, tell us about the formation of the Appalachian Mountains and Katahdin. Big question.
Wow.
Yeah.
Well, the whole event that I just described is part of the Acadian orogeny. So that's the main mountain building event. So like I said, most of these rocks formed during the Devonian, so about 400 million years ago. And so there's like a lot of tectonic activity, and a lot of them were slightly deformed. So you may have noticed earlier when I was showing the layers of the traveler rhyolite, they're not horizontal, which they would have been deposited, horizontally originally. Now they're slightly tilted because the area has been deformed a little bit. So yeah, there are a lot of deformation and erosion and uplift took place over those 400 million years. And I don't think geologists even know exactly what happened. But I think, like I said, the park as we see it today was really influenced by glacial erosion. And the deposits and landforms that we see today are more specifically from the last ice advance. So which started or culminated around 25,000 years ago and ended around 12,000 years ago. So those are really the high points in that history. But yeah, it's hard to tell exactly what happened at every stage, but those were the general most important steps in the park's geologic history.
Yeah. Thank you. That's a great answer to a big, complicated question. In terms, if you're interested in the history of the Appalachians, more broadly speaking, that extending well out of Maine, that actually the folks involved in the International Appalachian Trail are pretty incredible bunch of geologists, and have done a lot of work on the ancestral Appalachian Mountains, continuing on over into up through Canada and over into Northern Europe. And there's some pretty fascinating material there that you can learn from that group if you want to get involved.
Yeah, two former state geologists are on the IAT, I don't know, board, or they're very involved, and so yeah, there's a lot of good geology there, or good geologists involved.
Absolutely, yeah. So I think we've reached the end of our questions. So thank you all, everyone who asked those great questions. Thank you all so much. And thank you, Lindsay, for the absolutely outstanding presentation. That was excellent. And I know we're not going to be able to hear all of you in attendance clapping, but just please join me in giving a large virtual round of applause to Lindsay for doing such a great job. Thank you. Really, really appreciate it.
You're welcome. And please get a copy of this, digital or print. It has all the answers to any other questions that you have. And if it doesn't, you can contact me and I will try and point you in the right direction.
Thank you. Really appreciate you being so open to answering follow-up questions and spending your good chunk of your evening with us. So as I mentioned before we wrap up, this was the first webinar in our 2026 winter webinar series, and we do have several more coming up. So next Wednesday, January 21st, we have a webinar on some major updates to the park's reservation system. And our presenters for that will be Brian Bueller, who's the Park Services Manager, and Lori Morrison, the park's Director of Administrative Services. And these are the extremely talented folks who designed these improvements to the reservation system. And so you can get the inside scoop from the folks who made that happen. And that webinar is at 7 p.m. next Wednesday. Jam just put the link in the chat where you can go to our events page on our website and sign up to attend that next Wednesday if you're interested. On February 11th, we'll be having a webinar on the fossils of Baxter State Park, which are pretty incredible. You saw Pertica quadriferia on screen tonight. They are globally significant. And our presenter for that session is Seviajo, and she will be speaking at 7 p.m. on February 11th. And finally, March 11th, we're hosting a webinar on the alpine plants of Baxter State Park. Some of you may know Katahdin in particular is the largest concentration of rare and endangered plants in Maine, alpine species. And our presenters for that session are botanist Andrea Terrell from University of Maine and Nava Tabak from Baxter State Park. So join us, you can join us March 11th for that session. And as I said, you can register for all of those events on our website. Jam put the link to our events page in the chat, and you can just click that and sign up very quickly and easily by Zoom. So I want to thank again all of our members watching tonight for your support and for making programs like this possible. And if you're not already a member and you enjoyed our session tonight, please consider joining on our website, friendsofbaxter.org. Again, that link is in the chat, and you can click the top right corner of literally any page on our website, and it's pretty easy to find. We'd love to welcome you as a new member. So thanks again, Lindsay, for that amazing presentation. Thank you all for attending. Hope to see you next week for our next webinar. So good night, be well, and see you all next time.